Okay, these are going to be example problems dealing with refraction, and there might be a mention of reflection, but those are pretty straightforward answers. Here's the sheet. I know it says CP, but we're going to use these for all of the classes. When it comes to refraction, the problems are pretty straightforward, where we're just using the same Snell's law equation over and over again. All right, so I'm going to work through these one by one. I know I already have them worked out there. If you just look at that picture, that's fine. The first one, and you can follow along, this will be on the site, and you could copy one off if you'd like, or put it in Notability or however you like to do it. All right, so example one, I'm going to read it. It says, a light ray of wavelength 589 nanometers. Now sometimes they give the wavelength, but that's really irrelevant for us. All it's doing is giving us maybe like the color of light, but we don't need to use that number. It's traveling through air, which has an index of refraction of 1. You use the paper to look that up. The charts of indexes of refraction or indices of refraction. It's incident upon a smooth slab of flat crown glass. I don't have my other light, so I don't know if this is going to be dark or not. So here's my piece of crown glass. On the outside, the end value is 1. The crown glass, when we look it up, is 1.52, if I recall. Yep, 1.52. Not things you have to memorize, just charts that you need to look up. Light ray comes down, it strikes the glass. Now, we know if we go from a low to a high, it bends towards the normal. So this angle is going to be larger than this angle. So it says the flat slab of crown glass at an angle of 30 degrees to the normal. So what this is 30 degrees. So we'll call this N1 and we'll call this theta 1. Just make sure whatever we call 1s are on the same side. And then we'll call this angle our refracted angle, theta 2, and our crown glass, theta 2. And so what we're looking for is the refracted angle, theta 2. So we go N1 sine of theta 1 equals N2 sine of theta 2. Now I'm going to solve for theta 2. In the problems coming up, if I ever have to solve for theta 2 again, I'm just going to write down what it is. Okay, I'm not going to show all the algebra. So we divide by N2, and we get N1 sine of theta 1 over N2 equals sine of theta 2. And then I'm going to do inverse sine of each side. Some people will just solve it like this and just say sine of theta 2 equals. That's not solving for the angle though. All right. So this, and we have 1 times sine of 30 degrees. Now make sure that you see it's 30 degrees. So we need to make sure our calculators are in degrees. And when I calculate this, I get 19.2 degrees for theta 2. 19.2 degrees for theta 2. Yeah, it's going to be pretty dark. All right. So as far as the calculator, how do we put that in? Hopefully you'll be able to see this. I'm not sure. So I do not put the sine part in first. I just say 1 times, which I don't even put that in, right? If it's 1 times something, sine of 30 divided by 1.52. And I always set that equal sign normally on top. All right, and I get, for this in here, I get 0.329. And then I have to take inverse sine of my answer. And I get 19.2, thank goodness. All right, next one for our paper. It says, example 2, light of a wavelength, once again, same thing, is in a vacuum. Okay, now you notice this says air and this is a vacuum. The fact is air in a vacuum is very, very close to 1. A vacuum is exactly 1, and air is like 1.00029 or something like that. Okay, so you can go to 2 decimal places each time. for our index of refraction. It says it passes through a piece of fused quartz, and you're like, what is that? Just find it on the table, okay? And it tells us 1.458, okay, is the index of refraction. Find the speed of light. So the thing about example 2 and how it's different is that the other ones give you angles. If you notice in example 2, it doesn't give us an angle. And it also talks about the speed. What is the speed of light? Anytime you see that, you're going to use this formula right here. Okay? It's the index of refraction is equal to the ratio of the speed of light in a vacuum, c, divided by the velocity. And in this case, we're solving for the velocity. Trust me, the algebra works out that way. Velocity, this is a constant. It doesn't hurt to memorize it. 3.00 times 10 to the 8th, that's in a vacuum. And it tells us that the index of refraction of that, that fused quartz is 1.458. Okay. Remember, index of refraction is a ratio, so we don't need to worry about units because they would cancel out. They'd be the same unit. 2.06 times 10 to the 8th meters per second. One little thing to look for, whenever we have a velocity, I don't see how it's going to be outside of times 10 to the 8th, at least for what we're doing, okay? All right. Just so you remember, on the calculator, if we're going to type in 3 times 10 to the 8th, you know I like the EE, and we could just type it like that. That's 3.00 times 10 to the 8th meters per second. Okay, example 3. An optical fiber. So fiber optic cable. Okay, that goes in, and the index of refraction is 1.44. All right. So basically the setup we have, and it's a little bit different than I have drawn there, was for example 3. For example 3, we basically have a like a cable like this, and it's sealed off, and the light comes in and strikes the barrier, and it bends, okay, from the outside. So the way I draw this is I still tend to always draw it like this. This is our barrier, and on the one side we have air, and on the other side we have our, what's it called? Or it just says our optical fiber, and it gives us a value of 1.44. It also tells us that the angle that it hits at is 22 degrees, and we know once again that it bends towards the normal because we're going from low to high. So once again, we're solving for this, which is theta 2, and this will be theta 1. So from the previous one, without showing how to get there, example number 1, this is what it turned out to be, right? From Snell's law. And we plug our values in. I like my purple little Sharpie here. And we get a theta 2 equaling, what do we got here? 15.10, 15.1 degrees. Okay. I should have paid a little closer attention to what the question was asking. So the first question asked, in which direction does the light bend? And I already mentioned that. It's towards the normal because we go from a low number to a high number. It bends towards, if it was high to low, it would bend away like out this direction. We answered C, and then it says sketch a path of light as it changes media. from one medium to another, one substance to another. And so we did all those things. Example 4. Example 4 states, once again, light is traveling through the optical fiber and then it comes to the end. All right? So if you look at this, you might just like go back to the other one and write down some answers from that. You can't do that because it hits the end with a angle of 30 degrees. Okay? So it's the same type of problem. Up here though, my phone's ringing. Up here we have our index of refraction of 1.44. That's where we're starting because we're now inside the optical fiber. And then we're going to air outside. So here's my angle, 30 degrees. Now we're going from a high to a low. So it doesn't bounce this way or bend this way. It actually bends out that way. So we're going to have a larger angle here than we have up here. All right. And we're just going to take this same expression up here. And we get, if we plug in all of our numbers correctly, we get 46.1 degrees. And then part B says, how would your answer be different if the angle of incidence were 50 degrees? Okay, so all we'd have to do is put in 50 degrees. All right, we could do that. Up here, we'll just do this one with 50 degrees for theta 1. Let's see what we get. So 1.44 sine 50 divided by 1. Okay, now here's a little thing that we're going to get to. It says answer is 1.1. Then I'm going to take the inverse sign of my answer and I get air. Okay, so what does that mean? Some people think that you did it wrong or that I did it wrong. That's not the case. So remember when we had fiber optic cables, or I mentioned them earlier, there's a point here. As I change this angle, you're always going to have a little bit of this light reflect back into the medium, and some's going to refract out of it. You're going to get to the point though where you hit this angle, and at that angle, remember it's called the critical angle, nothing is refracted. Everything is reflected. So this is the case, all right? Now we're not saying it's 50 degrees, but we know it's somewhere between 30 and 50 degrees, okay? And I don't care what it is because it doesn't ask for that. But what I can say here is that it's totally, 2 L's, reflected. So we're past the critical angle, all right? Now, here we go. The last one. I started to draw it, and I actually wrote it on a whole separate sheet of paper. So if I decide, well, no, I could probably talk about it a little bit here. This will be fine. So here's my setup. M1, M2. It's kind of just a geometry thing. And remember that in a triangle, the angles add up to 180 degrees, and that's important. All right. So I think we could see this. So M1, M2, and there's an angle of 120 degrees between the two. Okay? So if an incident angle comes in here at 65, it bounces off at 65. Okay? Now what I'm doing is just looking at the mirror like this. And for some reason, this is how I drew my two mirrors. I mean, you could have drawn them like this, whatever. It doesn't matter. So this angle is 65, that angle is 65. This internal angle here has to be 25. 65 plus 25 equals 90. This right here is a 90 degree. So now I have 25, 120. And the question is, what is this angle then? So 25 plus 120, okay, plus whatever is equal to 180. So the answer would be 35, all right? So this right here is 35. Now I draw my normal perpendicular, so at a right angle to my surface. And the question is, find the angle the ray makes with the normal. So a lot of students will just write down 35 as their answer, but really what it wants is this angle. So 90 minus 35 equals 55. All right, so that's not too bad. I was thinking this was the problem that I'm going to pass out involves the distance between two beams. That's a whole nother ball game. All right. So those are 5 examples, and they're pretty much the same. I'm going to make another video with some of you are very familiar with the physics classroom online. Trust me, from the labs and such, I know. I'm going to do some extra examples from there.